week I told you that the next topic will be numerical integration. And we review some mathematical preliminaries of numerical integration. How to find the exact value of integral. And today we consider some techniques how to find the value of the integral numerically. And as usual, I consider some problem where we need to find the integrals, and in particular case where we need to find the integral numerically. Let's consider some example of real-life problem. The sheet of corrugated roofing is constructed by pressing a flat sheet into one. Those cross-section has a form of sine wave. So initially we have a flat sheet, for example, of aluminum, and as a final result, we should get a sheet those cross-section has a form of sine like this. And we know that the length of a corrugated sheet is 4 meters. So we should get a 4 meters long sheet. We know the height of each wave, 10 centimeters from the central line. And we know the length of each wave, period. For simplicity, assume that this period equals to 2 pi, approximately 6.2. And the problem is how to find the length of a flat sheet that we should take to do this corrugated sheet. And this problem, the problem of finding the length on the initial sheet, is one of determining the length of the curve given by the f of x equals to sinus x from 0 to 4. So we know that the cross section has a form of sine. We know the length. This length is 4 meters. But what is the length of initial flat sheet? We need to find the length of this curve. The length of this curve. And from mathematical analysis, we know that the length of the curve that defined by the function f of x equals to integral from a to b, from left point to the right point, 1 plus f prime of x in square, and square root of this. We should find this value. In our case, f of x equals to sinus x. F prime of x equals to cosine x. So we should find the integral from 0 to 4 square root 1 plus cosine square dx. So the problem of finding the length of the initial flat sheet is reduced to evaluating this integral. The sine and cosine are very simple functions with their good properties, but their calculation of the integral involves an elliptic integral of the second kind, which cannot be evaluated by ordinary methods. In spite of cosine is a very simple function, square root of 1 plus cosine in square, it cannot be found by elementary methods. But we can find this integral numerically. We can find the approximated value of this integral. And the methods for finding of such approximations are the topic of this lecture. On previous lecture, we consider that the precise, the exact value of the integral can be found by applying so-called Newton-Leibniz formula. Integral from a to b f of x dx equals to f of a, sorry, it's one mistake. I always forget to fix it in this presentation. Let me fix it right now. Because there is one simple mistake. Okay, let me type it right now. Integral from a to b f of x dx to f of b. Of course, f of b minus f of a, but not f of a minus f of b. This formula is wrong. This one is correct. Integral from f of x dx equals to f of b minus f of a, where f of x, f capital of x, is such function that f prime of x equals to f of x. This operation is called anti-differentiation. Well, to find the value of the integral exactly, we should find the antiderivative of a function. We consider a very simple example on a previous lesson. Suppose that f of x equals to x squared. What is the antiderivative of this function? We should find such function f capital of x such that f prime of x equals to f of x. F of x is x squared. That's why f capital of x equals to x cubed over 3. X cubed over 3 in general plus c, but for our case it doesn't matter. Well, for simple functions, for such simple functions like x squared, x cubed, x power n, sinus, cosine, we can find antiderivative very simple. There are very simple formulas for anti-differentiation, but in some cases we cannot find antiderivative. We cannot find it not because this antiderivative is very complex, but it's proved that this antiderivative doesn't exist. So no such function f of x for which f prime of x, f capital prime of x equals to f of x. And this is 2 examples. Cosine of 3 cosine x, cosine of cosine. From the first point of view, this function is very simple. And we can find derivative of cosine, but we cannot find antiderivative. And the same function, more or less the same, sine of exp. It's also, we cannot find antiderivative. We can find derivative, but we cannot find antiderivative. And there are a lot of elementary functions that do not have antiderivatives. Another simple example is e power x squared, exp of x squared. This function, again, I repeated, from the first point of view is very simple, and we can find a derivative, but we cannot find antiderivative. And that's why we cannot find the exact value of the integral using this formula. And the question is how to find derivative, how to find the integral in this case. How to find the integral for the functions which are maybe hard to evaluate, or maybe these functions do not have antiderivatives. The answer is the same as for integration. We can use interpolating polynomials to find derivative, to find the integral. We use interpolating polynomial to find derivatives. And on the same way, we can use the interpolating polynomial to find the integral. The approach is very simple. If we know f of x, where f of x is a complex function, for example, it's hard to evaluate, or it's this function doesn't have antiderivatives. In this case, we can replace replace f of x by another function g of x that approximates f of x well and is easy integrated. And after that, we can say, as far as f of x approximately equals to g of x, because g of x approximates f of x. I just reproduce here what's original on the slide. F of x more or less close to g of x approximates f of x. Then we can say that the derivative of f of x equals approximates g of x, and also the integral of f of x from a to b f of x approximately equals integral from a to b g of x dx, where the function g is the function that can be easily integrated. And polynomials are integrated perfectly. Polynomials are good candidates for the function g of x. And g of x can be a polynomial that interpolates f of x at a certain set of nodes. So the idea of for numerical integration is the same as for numerical differentiation. Let's take the set of nodes. Let's take the function values at these nodes. After that, let's interpolate the function. Let's find a polynomial. Then let's find the integral of this polynomial and compute the integral using Newton-Leibniz formula. And we get the approximated value for the function f of x. Suppose we want to evaluate the integral in the interval from a to b. And also suppose that we take these two values, these 2 points, A and B, as the nodes for interpolation. It means that we select A, we select B, we know the point f of A, we know the point f of B, this is f of A, this is f of B. After that, we can find, using these 2 points, Lagrange interpolating polynomial of the first degree, and find the derivative of this integral. In general case, we can take a lot of nodes between A and B. The set of nodes, 1, 2, 3, 4, 5, a lot of nodes. If we select n+1 point, n+1 nodes, in this case we can find the polynomial of the degree n, Then we can find the integral of this polynomial. We can find the integral of this polynomial. And as far as f of xi are constants and the variable is also only x, we can move this constant outside the sign of integration. And on this way obtain the formulas that can be used for any function f of x. Finally, the approximated value of the integral from a to b f of x dx approximately equals to the sum of the values I from 0 to n, the values of the function f of xi times some coefficient ai, where ai equals to the integral from a to b of Lagrange auxiliary polynomial Li of x. This formula is called Newton-Cotes formula if the nodes are equally spaced. And as example, let's consider their simplest case. Suppose that we have only two nodes, as I write on the board, A and B, two nodes. A equals to x0, x1 equals to b. In this case, we can find a Lagrange polynomial of degree 1 using these 2 points. And when we find it, we write auxiliary functions L0 of x that equals to b minus x over b minus a, and L1 of x that equals to x minus a over b minus a, and the coefficient a0 equals to integral from a to b L0 of x dx. The value of the integral equals to 0.5 times b minus a. Let's find this value. The result is written here on my slide. But let's find this value. Let's repeat all of these calculations. Integral from a to b. Integral from a to b. L0 of x dx. L0 equals to b minus x over b minus a. Dx. How to find this integral? The variable is x and b are constants. That's why I can move the constant outside the sign of the integral, and I have here 1 over b minus a, integral from a to b, b minus x dx. After that, the integral of difference equals to the difference of two integrals. One over b minus a integral from a to b dx minus integral from a to b x dx. Here b is a constant. B is a constant. B can be moved outside to the sign of the integral. And we have two very simple integrals. Integral from a to b dx. What is, so it means 1. So what function has derivative 1? Just x. X. And we have here b times x from, and substitution from a to b minus. Here we have x, and their antiderivative will be x squared over 2 from a to b. Now let's substitute these values, and we have 1 over b minus a, b times b minus a minus b squared minus a squared over 2. Well, after some simplifications, for example, here I have b squared minus a squared. B squared minus a squared, it can be written as b minus a times b plus a. I can move b minus a outside the brackets, and it cancelled with this term. It's cancelled, and I have here b minus b over 2 plus a over 2. B minus b over 2 equals to
Plus a.
So finally I have here b minus a over 2. The same value, 0.5 times b minus a over 2. And if I try to find the integral from L1x dx, the value f1, I obtain the same result, 0.5 b minus a over 2. If I substitute these coefficients a0 and a1 into the general Newton-Cotes formula, I get this result. That integral from a to b f of x dx equals to, approximately equals to, b minus a over 2 times f of a plus f of b. Very simple formula. Integral from a to b f of x dx approximately equals to b minus a over 2 f of a plus f of b. This is the exact value. This is approximation. You see that we can get approximation. We can get approximation to the real value of the integral in very simple way. We should just calculate the value of the function in the left point, at the right point, and apply this formula. And we get approximation to the real value of the integral. Before we solve some example using this formula, I want to show you the geometric interpretation of this formula. Let's look to this picture. And first, let's review that the value of the integral f of x dx has the following geometric interpretation. It's an area under the curve f of x. The exact value of the integral is area under the curve f of x. But we don't know f of x. We know only these 2 points, f of a and f of b. What we can do? We can draw a line. We can draw a line that passes through the points a and b. This line is a geometric interpretation of a polynomial of the first degree of interpolating polynomial P1. And we can say, okay, P1 interpolates f of x. P1 of x is a polynomial that is more or less close to the function. And the area under the polynomial between this line, between the polynomial of the first degree and their x-axis, this area will be more or less close to the area under the curve. This figure is called trapezoid. What is the formula for the area of a trapezoid? What is the formula of area of a rectangle? Do you remember? I ask all of the students who connect to our meeting. Do you remember the formula for the area of a rectangle?
Yes.
Well, and what is it? What is the formula of? If the one side of the rectangle is A and the another side is B, the area of a rectangle is A times B. Very simple. What about trapezoid? How to find the area of a trapezoid? The area of a trapezoid is the length of this side plus length of this side over 2 times this side times the length of this side. the average value of these and these times this side. And this formula b minus a over 2 times f of a plus f of b, it's the formula of the area of a trapezoid. F of a plus f of b are the length of these two sides over 2 times b minus a. B minus a is the length of this third side of a trapezoid. So we have that the area under the curve is approximated by the area of a trapezoid, as shown on this figure. Well, let's solve some practical exercises. I ask all of the students to take your pen and paper and find the value of the integral x squared from 1 to 2 dx. What I ask you to do first I ask you to find the exact value of the integral. How to find the exact value? We should know antiderivative. The function under the integral is x squared. What is the antiderivative for x squared? The antiderivative is x cubed over 3. Very simple. So the value of the integral is x cubed over 3 from 0 to 1. So f of x, f of 2 minus f of 1. Please substitute these values 2 and 1 and find their exact value for this integral. Do it, please. I ask all of the students, take your pen and paper.
Okay,
and
perfect.
find the value of the integral. Yes, it can be, as far as this is a very simple example. And if you substitute 2 in cube is 8 minus 1 over 3, it equals to 7 over 3. 7 over 3 is the exact value for this integral. Okay, now let's suppose that we don't know this formula, but we know this one. And I ask you to apply the trapezoid rule to find integral from approximated value of this integral. Now, you should use f of x under the function under the integral x squared. And a and b are 1 and 2. Please use these values and find their value where you want to. You can go to your home. Okay. Please find the value of the integral. Using a trapezoid rule. I hope you see it on a board, the formulas, and also you can see it on this slide. The trapezoid rule. Try to find the value of the integral. What is the value? Who find? Please, you can type your result in chat. You can tell me your results in by using your microphone. Integral from x squared, integral of x squared from 1 to 2 using trapezoid rule. Well, any results? But you can type it. You can find it here. You can find it here. B and A are 1 and 2. B minus A is very simple. It's written why you repeat it? I don't understand because I write it here. 4 minus 4, sorry, not minus, plus 4 plus 1. That's all. No, this is approximately equals. After that, exactly because we compute 5 over 2. This value is 5 over 2. Let's compare the results. Please sit down. We have two results. 7 over 3 and 5 over 2. Let me share full screen. Let me share the full screen. I start Microsoft Excel and let's compute these values into Excel and compare the results. The true value is 7 over 3. Oops. Equals to 7 over 3. Our approximated value is 5 over 2. And the error is the difference between real value and approximation. The error is 0.16 with minus. So the error is not very large, 0.16. And after that, let's consider this picture again. How to find this the value of the integral more precisely with a smaller error. The idea we can exploit here two ideas. The first idea is to increase the number of nodes for interpolation. We can take not 2 nodes, but 3, 4 nodes. But in this case, polynomial becomes a rather complex function. And it will be hard to find the integral of this polynomial. And another idea is to increase the number of nodes, but apply the trapezoid rule with a smaller step. Apply trapezoid rule with a smaller step. For example, we can take x0 equals to a, x1 as a middle point, and x2 equals to b. We compute one more point here, and we take 2 trapezoids. The first trapezoid built for the points x0 and x1, this trapezoid, and the second trapezoid builds with the points x1 and x2. And after that, I can say that the area under the curve will be approximated more precisely as the sum of the areas of 2 trapezoids in comparison with one Dutch trapezoid for the points A and B. So if I apply this idea for this function, for this simple example, I can say that integral from 1 to 2 f of x dx, it equals to sum of two integrals. Integral from 1 to 0.5 f of x dx plus integral from 0.5 to 1 f of x dx. And after that, I can apply the trapezoid rule separately for the first half and for the second half. As far as these points place with the same distance, the difference, or I'm really sorry. It should be, of course, 1.5 and 1.5 and 2, because the interval is from 1 to 2, from 1 to 1.5 and from 1.5 to 2. What is the length of b minus a over 2 here? What is b minus a in this example? 0.5 will approximately equals to 0.5 over 2, and in the first bracket, x squared (1 plus 1.5 and square). The second bracket plus 1.5 and square plus 4 plus 2 and square. So I apply trapezoid rule 2 times. First time for the first half, of this interval, and the second time for the second half, from 1.5 up to 2. Of course, this value is hard to compute in mind. Let me show you this computation in Excel. I use Microsoft Excel to compute it. Okay, let's again reproduce the exact value. Exact value is 7 over 2, and the approximated value in our case will be 0.5 over 2, 0.5 over 2 times 1 plus 1.5 times 1.5. 1.5 is in square. 1.5 in square plus 1.5 in square equals to 2 times 1.5 plus 4, right? And you see that the result of this formula will be more close to the real answer. The real answer is 0.333, and we have 2.37. You see that the error becomes smaller. And exactly, actually, the error becomes 4 times smaller. You see that in the first case, the error was 0.16 and here 0.04, 4 times smaller. This fact can be proved theoretically. It can be proved theoretically. Maybe I skip this proof. I skip this proof that if we this is the error term of the trapezoid formula, but this fact can be proved. Well, here I just want to show you that if we take the smaller step, the smaller distance between point, and after that summarize the values that we get on these intervals, we will find the value of the integral with high precision. And now let's consider one more rule of integration. I only show you this rule on a here. Suppose that we have 3 points. X equals to A, X2 equals to B, and X1 a middle point that is placed between A and B, where H is B minus A over 2. H is B minus A over 2. So it means that I consider the same 3 points, X0, X1, and X2. Now we consider the second way how to decrease their error. And the second option is to consider the Lagrange polynomial of degree 2. To build this Lagrange polynomial, we can build auxiliary polynomials L0, L1, and L2. After that, we can find the integrals of these polynomials A0, A2, and A1. I skip this integration because this integration is complex. And finally, we get this very short and simple formula. Let me reproduce this formula on the board. Let me reproduce this formula here, or here below the trapezoid rule. Integral from A to B, where A equals to x0, B equals to x2. Integral from A to B, f of x approximately equals to h over 3, where h is a half of b minus h over 3 times f of x0 plus 4 f of x1 plus f of x2. Again, what we do, we compute the function value at these 3 points, f of x0, f of x1, f of x2. H is step, 1/2 of b minus a, and after that we can apply this formula. This formula is called Simpson's rule. And the geometric interpretation of Simpson's rule is written here on this slide. We take 3 points. And there is a curve of function f of x. We don't know it. But using these 3 points, we can find a polynomial of degree 2, P2. And we can say that the area under the curve will be more or less close to the area under the polynomial. Let's apply this formula to our case. Let me done all the computations in Excel again. What I should write here? What formula I should write here? H over 3. H is a step, 1/2. H over 3 times f of x0. F of x0 is 1 plus 4 f of x1 plus 4 f of x1. F of x1 is 1.5 times 1.5 plus f of x2 plus 4. Excellent result. Please look to this excellent result. We get exact value, 2.3. This formula gives us the exact result. The error is 0. Why? Why we get this excellent result? The reason is written here in this error term. As the situation is exactly the same as for numerical differentiation formulas. The error term has 2 parts. The first part, it depends on h, on the step. And the second part depends on the derivative of the function. H is a positive value, small but positive. So h power 5 never be equals to 0. But the fourth derivative, f of x, in our case equals to 0. In our case, f of x equals x squared, and the fourth derivative of x squared equals to 0. That's why we get exactly 0. The exact value is 0. Well, finally, let's consider one more formula, the last formula, so-called middle point rule or rectangular rule. Let me draw the same picture. Let me reproduce the same picture. For example, this is A, this is B, this is H, the step. Suppose that this is f of x, f of b, this is the function, and the area under the curve is the value of the integral. So this area can be approximated by the area under this rectangle. I can take the middle point, I can take this rectangle, and I can say rectangle is a very simple figure, and I can I can calculate the area under the area of this rectangle is very simple. This is the value at the middle point, value of the function. This is h, the step. And the area of under the curve can be approximated by the area of this rectangle. Let's apply this formula for our case. Well, what is the step? What is the distance between points? The step is 1. What is the middle point? Middle point is 1.5. Point is 1.5 in square. So the rectangular rule, the middle point rule, is this. And we get the value that is somewhere near the true answer. True answer is 2.33, and the middle point rule gives us 2.25. Well, finally, I can say that we consider 3 rules for numerical integrations: trapezoid rule, rectangular rule, and Simpson rule. Of course, the best one is simple Simpson's rule, but sometimes it's hard to apply Simpson's rule because we must know 3 points, 3 values of the function to apply Simpson's rule. To apply trapezoid rule, we should know just 2 values, and for middle point rule, it's enough to know only 1 value of the function. It's enough to know only 1 value, and I can apply this rule. I can find the value of the integral. So if the function is very hard to evaluate, or if we know just this 1 value, we can apply only the middle point rule. Well, I think that's all that I want to say about the numerical integration. As a homework, I ask you to solve. I ask you to find the values of this integral. Let's consider the integral under the letter A. Exercise 1 under the letter A. Find the value of this integral using middle point rule, trapezoid rule, and Simpson's rule, and compare the results with the exact value of the integral. I will send you this presentation later today. I will send you the video file. Now, let's finish our lesson. Let me stop recording.